Hey everyone. We're going to start our first video on Unit 5A, which is going to be concerned with infinite series, on basically just a few definitions of things related to series and sequences, and just going over a few keywords. We will end the video though with actually one of the first real useful tools we have in assessing both series and sequences. So let's go ahead and get started. So first, let's go over a couple definitions. And the first ones we want to distinguish between are what is a sequence and what is a series. So as you can see up here, let me get some ink. Going to try the ink with the mouse, so this may be interesting. This is a sequence, and you notice that we call it a sub n. Now that sub n down there, for those of you that are familiar with computer programming, sometimes this is called a counter. So if you're in like a for loop or a while loop or something like that, you want to keep track of how many times you've done a particular iteration. Well, that value n is very similar. So basically the value n will start at 0 or 1 or 2 or just some kind of starting number. And it'll go basically all the way up to some other number. Now that other number could be infinity. But basically it'll go up in iterations of 1 every single time. So as you can see in this sequence right here, we start with n equals 0, then we go to n equals 1, n equals 2, all the way out to n equals, some number. So basically a sequence is just an ordered collection of all of these numbers. And a sequence is calculated using some function of that counter n, as we can see right here. So in this example, if our sequence is n squared over n plus 1, well, we start out by plugging in n is equal to 0, and if we do that, we get 0. Then we can plug in n equals 1. If we do that, we get 1/2. When n equals 2, we get 4/3. When n equals 3, we get 9/4. And then we can just keep going. So these are all the numbers in our particular sequence. So yeah, really just for now, think of a sequence as kind of like maybe like a deck of cards or something like that. Where you have this particular order of all 52 cards in the deck, but obviously we don't need to have 52 elements in any particular sequence. So sequences are actually not a very big focus of this class. You really just need to know basically what they mean, what I just described to you right here. What's more important is how we can talk about the role sequences play in something called a series. Now in this case, a series, I call this S sub n, and really this should be a capital N right here. That's a typo, so I'm sorry about that. But anyway, what this series means is that we just add up all of the terms in the sequence, in this case up until capital N terms. Now, if you guys have never seen series notation before, again, if you've had any kind of computer programming, this is going to be very similar to keeping track of a counter in a for loop or a while loop. But we start with that value little n equals 0, and we go up values of 1 until we get to some value which we call capital N. And what a series does is it just sums up all of those elements in the sequence. So in the sequence where we just ordered all of those elements, in the series we actually add all of them up. Okay? So for an example, if we start with the same sequence we had before, our series would be just adding up all of the elements of that sequence. And so there you go. So if you understand sequences, series are just adding up all of the elements in a particular sequence. So now let's talk about what an infinite series is. So an infinite series, as you'll notice, the big difference between this slide and the last slide is that capital N, basically the number of terms we're adding up in the sequence, that actually goes to infinity. Now some people, when they first see this, they're kind of confused because this presents a little bit of a logical dilemma. And it's that, well, if you're adding up an infinite amount of things, doesn't that just always go to infinity? Won't you always keep growing and keep growing? And the answer is half of that's right and half of that's actually not so much right. Yes, you will keep growing and growing and growing, but you may keep growing and growing and growing without bound, which is something which we call divergence, which in math is generally bad. Or we keep growing and growing, but we grow at such a decreasing rate that eventually each term in our growth becomes completely insignificant with respect to the previous term, or our growth becomes so small that we're never able to grow above a certain value. So that's called convergence, and that's good. We want that to happen. So basically, an infinite series is just a regular series, but you just go out to an infinite number of terms. Okay, and that's mainly what we are going to be talking about in this unit. Now, there's another definition called a partial sum. So a partial sum, we'll say the capital Nth partial sum of an infinite series represents the value that that series has if we go to capital N terms right here. So again, if we're using the same sequence, n squared over n plus 1 we had before, we would have our 0th partial sum means, okay, well, we're only going out to the 0th term, which in this case is just the first term in the sequence, so that would just be 0, okay? Remember, if the sequence is n squared over n plus 1, plug in 0 into that equation and we'll get a sub 0 is equal to 0, okay? Now, if we go, let's say the first partial sum, if we go to capital N equals 1, well, that means we're going to sum up the 0th term and the first term. So we would add 0 plus 1/2 to get 1/2 coming out of that. Now, as you can see where we're going with this, if we looked at the second partial sum, we're summing up to the second term, meaning we go a0 plus a1 plus a2, which would end up giving us 11/6. So as you can see right here, partial sums, it basically, what it means is really all there in the wording. The word partial. The word partial means not complete. So we're not summing all the way out to infinity. We're summing out to some finite number. And every time we run the sum to a certain number, the value of the sum is going to change. As we saw here, the partial sum went from 0 to 1/2 to 11/6. And then if we did, for example, the third partial sum like that, we would get an even different number because we would add that third term, a sub 3. Okay, so now we have some of our important definitions that we got to go over. The next definitions we go over, though, are going to be the most important ones that we're going to spend the bulk of this unit especially discussing. And actually, before I do that, I'm sorry, I'm skipping ahead one slide. We also have some properties of series, and as you'll notice, these are very similar to the properties that we've seen all the way through limits, derivatives, and integrals, in that the sum of two series is equal to the individual sums of each of the series added or subtracted together. And then if we have a constant inside the series, we can always just pull that constant out and everything works. So in this case, we have a n, b n, and c n are all sequences. And so if we multiply a constant by those sequences, or if we add those sequences together and do a sum of them, we can do these various operations. Now, this should come somewhat intuitively at this point. But just so you know, we might be using some of these tools at various points throughout discussing this unit. Okay, now back to what I told you are the two most important things we're going to talk about. That's this concept of convergence and divergence. So remember I said convergence is basically when we settle on something, okay? So we have two different types of convergence right here, one for sequences and one for series. So sequence convergence basically means if we go out to an infinite number of our terms, eventually all of those terms just settle on the same number. We call that number L. So in this case, the sequence, the numbers in those sequence are settling on something, so we say this is a sequence that converges. Now, series convergence is a little bit different. If we have a series, again, that's given by a sum of a particular sequence, what series convergence means is that if the series, when we go out to an infinite number of terms, converges to a value which we call m, then the series converges. Now, realize this is different than sequence convergence. So we can have a convergent sequence, but a non-convergent series. So one example of that is if we looked at the sum of, if our sequence was, let's say, just 1, we'll go from n equals 1 to some number infinity. Well, if we go out and write out the terms in that sequence, that'll just be 1, and I'm sorry I'm drawing with the mouse, this is very difficult, 1 plus 1 plus 1, and then on off into infinity. We're just going to keep going. So in this case, our sequence, well, it converges to 1 because it's always going to be the value of 1, but the series itself actually doesn't converge because it never settles on a number. It just keeps growing and growing and growing and growing and growing. We're just adding 1 to every other term. So what we notice basically must happen is that if we want a series to converge, we absolutely have to have that sequence converge, but it must specifically converge to the value of 0. And that kind of makes sense because if our a sub n term goes to 0 as n goes to infinity, then in our series we're just going to be adding eventually 0 plus 0 plus 0 plus 0. And if we're just adding 0 to something, we're not changing it. Therefore, it's settling on something. So, on the contrary, if we talk about divergence, that's just the opposite. That's when a series or sequence doesn't end up settling or something. So for a sequence, if our nth term doesn't settle on a number, if it just goes off to infinity eventually, or even if it really just keeps growing without bound, basically if it just doesn't go to that number that we called L, then the sequence diverges. And in a series, if we take the series out to an infinite number of terms and that grows without bound, it goes to infinity, then the series diverges as well. So in math, divergence is very bad. As you can tell, we don't like it when things go off to infinity. We want to make sure things converge. So a big portion of what we study in infinite series is whether series converge or whether they diverge. And we've just realized right now a very important test. This is our first test that we can use to assess whether a series will diverge. It does not tell us if a series converges. It just tells us if a series diverges, and I'll talk about that in a little bit later. But basically, if we go out to an infinite number of terms in our sequence, and that infinite term in our sequence is not equal to 0, our series is always going to diverge. And again, that was just like what I was saying on the last slide. If a series is going to converge, eventually when we go out to an infinite number of terms, we should start seeing 0 plus 0 plus 0 plus 0, so it's settling on some number. Now, if that number is not 0, it doesn't matter how small it is, if it's not going to 0, we have no chance of that thing converging, or of that series converging. So what this is called is the test for divergence, and it's pretty much always the first thing we do whenever we encounter a series if we want to see whether it converges or diverges. Now, the test for divergence, realize it's called test for divergence. It's not called test for convergence. If we happen to get that the limit, like on the previous slide, if this limit happens to equal 0, that actually doesn't tell us that the series converges. It just tells us that the series might converge or it might diverge. However, if that limit is ever not equal to 0, we know with absolute certainty that the series itself is going to diverge. So let's look at a couple examples of this. So let's look at this particular series, and what I want to ask is, does this series diverge? So try to pause the video and figure that out. Okay, if you use that test for convergence we talked about previously, what you'll get is that we want to evaluate the limit of our sequence right here as our value n goes to infinity. And if we do that, well, we'll get infinity over infinity, so we got to use L'Hopital's rule. Remember that nifty little rule? We take the derivative of the top divided by the derivative of the bottom. If we take that derivative with respect to n, we end up getting the limit is just 1. So this limit is not equal to 0, so therefore we know with absolute certainty that that series is going to diverge. All right, so let's try one more. So if we get a series like this, try to figure out if that one will diverge. All right, so if you do the test for divergence on this one, you'll end up getting that, okay, the limit is 0, so that's good, but remember, this is called test for divergence. It's not called test for convergence. If we get that the limit of our sequence as n goes to infinity is equal to 0, that actually doesn't tell us anything. It doesn't tell us whether it converges. It doesn't tell us whether it diverges. Remember, all we're looking for is for that limit to be non-zero, because if that's true, we can immediately say, oh, okay, this series diverges. Let's not waste our time with this thing. So I told you I'd give you an example of this concept right here, of the fact that just because a sequence ends up going to 0 in infinite terms, that doesn't necessarily mean it converges or diverges. So what I have right here, and you can plot series in Desmos, and these are plots of two different series. So let's look at this red series first of all. We have the series from n equals 1 to x, where in this case, if we tick along our x-axis, that means we're just going out to an infinite number of terms, basically, in that series. So as x goes to infinity, we approach an infinite series. And our sequence is 1 over square root of n. And notice that this red line, this represents each partial sum of the series. Okay, so as we go further and further and further towards infinite terms, you can see that this thing just keeps growing and growing and growing and growing. And even when we zoom out a lot and it looks like it flatlines, if you keep going out, it's actually not flatlining. It's still steadily rising and rising and rising. If you don't believe me, plug this into Desmos. You can waste 6 hours if you want to, going off as far as you can to infinity. This thing is never going to settle on a number. It's actually just going to keep growing. So this red series here, the first one we've shown, is actually a divergent series. But if you plug in, n is equal to infinity in 1 over square root of n, you're going to get that that goes to 0. So this is a case where our sequence ends up going to 0, or the nth term in our sequence goes to 0 as n goes to infinity, but the series itself still diverges. Now, this next one we have down here is a different series, 1/2 to the n minus 1, and it turns out that if you look at this blue line, well, it kind of looks like that blue line actually really quickly settles on a particular number, and it turns out it does. This is actually a convergent series. If we highlight this line y equals 2, you can see that the series settles exactly on that number. And if we go out, like I said, you can go home, spend 6 hours trying to break Desmos going as far as you can, but you'll never see the blue line go over that green line right here. In fact, it becomes flush with it, because this particular series, 1/2 to the n minus 1, is actually something called a geometric series, and at that, it is a convergent geometric series, meaning that if we go out to an infinite number of terms, the series itself eventually settles on something. Now again, if we plug in n equals infinity into this equation, well, 1/2 raised to the infinity, that's also going to go to 0. So here we have two series that go to, or two sequences, I'm sorry, that go to 0 in their infinite terms, but one of them represented as a series is a divergent series, and one of them is a convergent series. And so really this is what we're going to be focusing on in this entire unit, is we're going to be given various types of series, and what we want to assess is, does this series converge or does this series diverge? In the next video, we will go over one of the most simple tests that we can use to test for this. So I will see you in that video.